Our universe should be a blank and empty void. Yet here we are, surrounded by galaxies, stars, planets, and life itself. The greatest mystery in all of science is not how the universe began, but how it became so richly complex. The prime suspect for this cosmic transformation is a single, profound event called symmetry breaking. It happened in the first fleeting moments after the Big Bang, and it may have written every physical law and shaped every particle in existence. By the end of this exploration, you will understand why many physicists consider this the most important event in the history of everything. We will uncover how a state of perfect uniformity shattered to create a world of difference, and we will examine the startling evidence that this process left behind. What does it mean that our entire reality might be built on a foundation of cosmic imperfections? To grasp why this breaking was so monumental, we must first understand what was broken. In that first indescribable flash, the newborn universe was not just hot and dense, it was perfectly symmetrical. In physics, symmetry is not merely about visual balance, like a snowflake. It is a deeper, more powerful principle. It means that the fundamental laws of nature remain unchanged, even if you rotate the entire cosmos, or look at it from a different point in time, or swap every particle for its antiparticle. In that initial state, the four forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were not separate. They were one single, unified superforce. The particles that would later become quarks, electrons, and photons were all identical, indistinguishable from one another. There were no differences, no distinctions, no unique identities. Think of it as a landscape of pure potential. Picture a vast, perfectly smooth, and utterly featureless plain, stretching to infinity in every direction. There is no north or south, no hill or valley, no landmark of any kind. Every point is exactly the same as every other point. This is the ultimate symmetry. A state of maximum potential energy, but with absolutely nothing to define it, no way for anything interesting to happen. In such a world, nothing can truly exist because existence requires difference. A universe in perfect symmetry is a universe without form, without structure, and without a story. It is the blankest possible canvas, waiting for the first, crucial flaw to appear. But a landscape of perfect, featureless potential is a precarious place to exist. That initial state of flawless symmetry was, in a deep physical sense, unstable. It was like balancing a pencil perfectly upright on its tip. In theory, it's a possible state, but in reality, the slightest breath of air, the tiniest vibration from a passing truck, will cause it to topple. The universe experienced its own version of that passing truck. As it expanded from that initial point of infinite density, it began to cool at an unimaginable rate. This cooling changed everything. The energy that once bound the four forces into one unified superforce began to drain away, and the smooth, featureless plane of the early cosmos began to develop subtle wrinkles. These wrinkles were quantum fluctuations, the inherent jitteriness of reality at the smallest scales, where particles pop in and out of existence even in a perfect vacuum. In that ultra-hot, ultra-dense beginning, these fluctuations were smoothed over almost instantly, but as the universe cooled, they gained a foothold. They became the seeds of imperfection. Our most advanced theories in particle physics and cosmology don't just allow for this instability, they demand it. The mathematics itself shows that the symmetric state was a high-energy configuration, like a ball perched at the very top of a hill. It might stay there for a fleeting moment, but it cannot remain. Any nudge, and it will roll down into a lower energy state, a valley of stability. The cooling universe provided that inevitable nudge. setting the stage for a cosmic transformation more dramatic than any supernova, a fundamental shift in the very fabric of reality known as a phase transition. This inevitable roll into a new state is what physicists call a cosmic phase transition. You have seen this process countless times in your own life. Take a pot of water and begin to boil it. At first, the water is a uniform liquid with molecules moving in every direction equally. It is symmetric in its chaos, but as the steam rises and cools, it undergoes a phase transition. It condenses back into liquid water droplets. If you cool it further below the freezing point, another, more dramatic transition occurs. The randomly jostling liquid molecules suddenly lock into a rigid, crystalline structure, ice. In this new state, the full rotational symmetry of the liquid is broken. The ice crystal has a specific, fixed orientation. Pick it up and turn it, and it looks different. The underlying laws of physics governing the water molecules haven't changed, but the stable arrangement they have settled into has less symmetry than before. The universe underwent a similar, but far more fundamental, transformation as it cooled from its unimaginable birth. The super-hot, symmetric state, where all forces were one and all particles were identical, became unstable. The universe froze into a new, stable configuration. In this new reality, the four fundamental forces were now distinct. Gravity had peeled away. The strong nuclear force which binds atomic nuclei became separate from the weak nuclear force which governs radioactive decay. Electromagnetism emerged with its own identity. This was the first and most profound breaking of symmetry. The particles that once were all the same acquired unique masses and charges, becoming the quarks, electrons, and neutrinos that would eventually build atoms. The critical thing to understand is that the original symmetry was not erased or destroyed. It was hidden, locked beneath the surface of this new, frozen reality. Its effects are permanently imprinted on everything. The specific way the symmetry broke determined the strength of every force, the mass of every particle, and the very rules of chemistry that allow stars to shine and planets to form. Our existence is a direct consequence of that particular cosmic freeze, a single path chosen from an infinite field of perfect, featureless possibility. This cosmic freeze had one particularly spectacular consequence, one that touches every single thing that has ever had substance. It created the very concept of mass. To understand how, we must visit the most famous and successful example of symmetry breaking in all of physics, a discovery that earned a Nobel Prize. We call it Electroweak symmetry breaking. In that first unified state, the electromagnetic force and the weak nuclear force were not two separate things. They were two faces of a single, elegant force, the electroweak force. The particles that carry these forces, the photon and the W and Z bosons, were also identical, massless siblings racing through the hot universe at the speed of light. But as the temperature plummeted, something extraordinary happened in the vacuum of space itself. A new field, now known as the Higgs field, underwent its own critical transition. Think of the Higgs field not as a thing made of particles, but as an invisible property of empty space, like an unseen ocean filling the entire cosmos. In the extreme heat of the beginning, the value of this field was zero everywhere. The ocean was perfectly calm and flat. But as the universe cooled past a critical threshold, this field suddenly shifted. It settled into a new, stable state where its value was no longer zero. Every single point in the universe, every cubic centimeter of what we call empty space, became filled with this non-zero Higgs field. It was as if the entire cosmic ocean developed a uniform, gentle depth. This was a profound breaking of symmetry. The empty vacuum was no longer featureless. It now had a specific, fixed property. And this new feature of reality had an immediate and dramatic effect on the particles moving through it. Particles that interact strongly with this pervasive Higgs field, like electrons and quarks, began to feel a kind of resistance as they tried to move through it. This resistance is what we experience as inertial mass. The more a particle interacts with the field, the more sluggish and heavy it becomes. An electron has a certain mass because it is constantly bumping against this invisible cosmic medium. A quark has a different, larger mass because its interaction is more intense. But here is the beautiful asymmetry. Some particles, like the photon, do not interact with the Higgs field at all. They simply do not feel it. So, when the symmetry broke, the photon remained massless, forever traveling at the ultimate speed limit of light. Its siblings, the W and Z bosons, did interact, and they suddenly became incredibly heavy, which is why the weak nuclear force has such a short range. In one sweeping event, the uniformity of the electroweak force was shattered, giving us the distinct electromagnetic and weak forces we see today, and crucially, endowing most of the universe's building blocks with the gift of substance. Without this specific breaking, particles would have no mass. They would all zip around at light speed, never clumping together. Atoms could not form. Chemistry would be impossible. Stars and planets would never coalesce. The diversity of our material world, from the carbon in your cells to the iron in Earth's core, is a direct and stunning byproduct of a single flaw that appeared in the fabric of empty space itself. But the symmetry breaking that gave particles mass was not the first. It may have been preceded by an even more dramatic event, one that shaped the very geometry of the cosmos. The universe we see is remarkably uniform. No matter which direction you look, the distant reaches of space display the same temperature and the same density of galaxies to an astonishing degree of precision. This presents a profound puzzle. How did regions of space now billions of light years apart, regions that could never have exchanged heat or information, come to be in such perfect thermal agreement? The leading answer is a theory called cosmic inflation. This idea proposes that a fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion. For a fleeting instant, a patch of space smaller than a proton was stretched to a size larger than our entire observable universe. This solves the uniformity problem beautifully, because everything we see today was once crammed into a tiny, causally connected region that had time to even out its temperature before being blown apart. But what could have powered such an impossible growth spurt? The answer points back to symmetry breaking, this time involving a hypothetical field known as the inflaton. In the earliest, hottest moment, this field was trapped in a state of high potential energy, like a ball held up on a high plateau. This energy acted as a form of negative pressure, causing space itself to stretch at an accelerating rate. But this state, too, was unstable. As the universe cooled, the inflaton field underwent its own symmetry-breaking transition. It rolled down its energy landscape, settling into a lower, stable valley. When it did, the tremendous stored energy was released in a flash, flooding the universe with the hot, dense soup of particles that would become the starting point for the Big Bang we traditionally discuss. This event broke the symmetry of space-time itself. Before inflation, the microscopic universe was a quantum foam, with no clear sense of scale or smooth geometry. The inflationary expansion ironed out all the wrinkles, creating the vast, flat, and uniform stage upon which all later cosmic drama would play out. But it did not iron them out perfectly. Inherent quantum jitters in the inflaton field were stretched from the microscopic to the cosmic scale, imprinting minuscule variations in density onto the fabric of space. These imperfections, these cosmic seeds, were the direct result of the symmetry breaking that ended inflation. They are the gravitational fingerprints that, over billions of years, would attract matter, growing under their own gravity to become the first stars, the majestic galaxies, and the vast cosmic web we observe today. Our entire cosmic structure, from the largest supercluster to the smallest dwarf galaxy, may owe its existence to the quantum tremors of a field finding its stable state in the first unimaginable fraction of a second. Yet another symmetry had to break for our reality to emerge, one that determined the very stuff we are made of. According to our best theories, the Big Bang should have produced matter and antimatter in perfectly equal amounts. For every quark created, an anti-quark should have been its mirror twin. This presents a terrifyingly beautiful symmetry, but also a cosmic dead end. When a particle of matter meets its antimatter counterpart, they annihilate in a flash of pure energy, leaving nothing behind. If the universe began with perfect balance, all of those pairs should have mutually destroyed one another, leaving a vast, empty cosmos filled with nothing but fading light. There would be no residue, no leftover material to build galaxies, stars, or people. The fact that we are here, that anything made of matter exists at all, is screaming proof that this symmetry was broken. Somehow, for every billion annihilations, a single particle of matter survived. That 1 in a billion imbalance is everything. All the stars, planets, and life across the entire observable universe are built from that tiny, miraculous surplus. Physicists call the process that generated this excess baryogenesis, the genesis of baryonic matter, the protons and neutrons that form atomic nuclei. The question is, what tipped the scales? The answer appears to lie in a subtle but profound violation of another fundamental symmetry, known as CP Symmetry. This is a combination of two ideas. Charge conjugation symmetry, or C, means the laws of physics should be the same if you swap every particle with its antiparticle. Parity symmetry, or P, means the laws should be the same if you view the universe in a mirror, flipping left and right. For a long time, physicists believed nature respected both these symmetries. But experiments in the mid-20th century revealed something astonishing. Certain rare processes involving the weak nuclear force violate this combined CP symmetry. In essence, the universe treats matter and antimatter not as perfect mirrors, but with a slight, inherent bias. It has a tiny preference for one-handedness over the other. Now, imagine the universe cooling through one of its early phase transitions. If conditions were just right, and this CP violation was in play, the processes that created and destroyed matter and antimatter could have become slightly out of sync. The creation of matter might have been ever so slightly more efficient, or the destruction of antimatter a tiny bit faster. Over the entire seething, energetic volume of the early cosmos, this minute statistical bias could have yielded that crucial 1 part in a billion excess of matter. When the great annihilation finished, that faint residue was all that remained. It was the seed of all structure. Without this broken symmetry, the universe would be a featureless bath of radiation, a monument to perfect balance and total emptiness. Our existence is therefore built on a triple foundation of cosmic imperfections. Symmetry breaking gave forces their identities, gave particles their mass, and then, in a final critical act, gave matter its enduring victory over annihilation. This cascade of cosmic transformations did not happen all at once. It unfolded in a precise sequence, a step-by-step freezing of reality as the temperature of the universe plummeted. Each step locked in a new set of rules, carving distinct domains of physics from the original unified whole. The first major division occurred at an energy so colossal it defies human intuition, a moment known as the Grand Unified Theory, or GUT scale. In this unimaginably hot and dense environment, just a sliver of a second after the beginning, 3 of the 4 forces were still one entity. The strong nuclear force which binds quarks together inside protons and neutrons was fused with the electroweak force. There was no distinction, but as the expansion continued and the temperature fell past a critical threshold, this unified force became unstable. The symmetry between the strong force and the electroweak force broke. Think of it as a special kind of crystal forming from a cooling liquid. The original, more symmetric state could no longer be maintained. The strong force peeled away, becoming its own separate interaction with its own unique carriers, particles we call gluons. This established the first major border in the laws of physics, the realm of the incredibly small, the interior of atomic nuclei, now operated under a different set of rules than the rest of the universe. This separation was absolutely vital. The strong force's unique property of getting stronger with distance is what locks quarks permanently inside protons and neutrons. Without this specific breaking, atomic nuclei could never have formed, and the periodic table of elements would be empty. With the strong force now on its own, the remaining electroweak force held sway. But this union, too, was temporary. The universe continued to cool and expand. When the temperature dropped to a point about 1 trillion degrees Celsius, a mere 10 to the minus 12 seconds after the Big Bang, the next great freezing occurred. This was the electroweak symmetry breaking we touched on earlier, driven by the Higgs field. In this event, the single electroweak force split into the two forces we recognize so clearly today, electromagnetism and the weak nuclear force. This was not a gentle parting. It was a dramatic change of state that altered the very character of empty space. Before this break, the particles that mediated these forces, the W and Z bosons and the photon, were all massless and interchangeable. Afterward, the photon remained massless, becoming the carrier of the long-range electromagnetic force that holds atoms together and brings us light. The W and Z bosons, however, became incredibly heavy, which confined the weak force to an extremely short range, effective only inside the nucleus. This breaking created the fundamental asymmetry that allows chemistry to exist. The weak force's short-range nature is crucial for processes like nuclear fusion in stars, while the long-range reach of electromagnetism governs the behavior of atoms and molecules. It wrote the rulebook for how matter interacts on almost every scale we directly experience. Gravity, the most familiar force of all, is the great outlier in this story. Our best theories suggest it may have separated from the other forces at the very earliest moment, perhaps at the instant of the Big Bang itself, at the Planck scale where space and time as we know them break down. Its story is still being written, waiting for a theory of quantum gravity to fully explain its place in the initial symmetry. What we are left with today is a layered cosmos, a universe of frozen accidents. Each symmetry breaking, each phase transition as the universe cooled, locked in a specific set of physical laws for a specific domain. The strong force governs the quantum world inside the nucleus. The electroweak force, now split, dictates atomic physics and chemistry. Gravity shapes the architecture of planets, stars, and galaxies. These are not separate universes, but different floors of a single cosmic building, each with its own rules established during a rapid-fire series of freezes in the first fleeting moments of time. The profound mystery is why these freezes happened exactly as they did, producing this particular set of forces with these precise strengths, a combination so exquisitely tuned that it allows for complexity, chemistry, and ultimately, us. The universe was now a seething sea of particles with mass, but the recipe for solid matter was still incomplete. The next critical transition would forge the very building blocks of atomic nuclei, locking away the fundamental ingredients of matter forever. This event is known as the quark confinement transition, governed by the laws of quantum chromodynamics. In those early, unimaginably hot moments, the strong nuclear force had already separated as a distinct entity. But its behavior was utterly alien compared to what we see today. The cosmos was filled with a state of matter called the quark-gluon plasma. In this primordial soup, quarks and the particles that carry the strong force called gluons roamed freely. They were not bound together. It was a chaotic, energetic medium where the fundamental constituents of protons and neutrons existed independently, like individual ingredients swirling in a boiling pot before they combine into a finished dish. This plasma represented a symmetric state for the strong force, the property that gives quarks their color charge, analogous to electric charge but far more complex, was freely exchanged. There was no permanent structure, only a frenzied, unconfined dance. But as the universe continued its relentless expansion and cooling, crossing a temperature threshold of about 2 trillion degrees Celsius, the nature of the strong force underwent a dramatic change. The quark-gluon plasma underwent a phase transition. It was as if the boiling pot suddenly cooled and the ingredients irreversibly fused. The force between quarks, carried by the exchange of gluons, possesses a unique and counterintuitive property. Unlike gravity or electromagnetism, which grow weaker with distance, the strong force behaves like an unbreakable rubber band or a tube of infinitely strong glue. When quarks are close together, the force is relatively weak, allowing them to move almost freely, but try to pull them apart, and the energy in the gluon field between them increases dramatically. So much energy builds up in the space between separating quarks that it becomes energetically favorable for that energy to spontaneously create a new quark and an anti-quark pair from the vacuum itself. The original quarks never get isolated. They instantly find new partners. This is the principle of confinement. Quarks are forever imprisoned in groups of 2 or 3. They can never be observed in isolation. As the universe cooled through this transition, every quark and anti-quark in that seething plasma found itself suddenly and permanently bound. Triplets of quarks locked together to form protons and neutrons. Quarks paired with anti-quarks formed particles called mesons. The age of free quarks was over in an instant. The symmetric, free-flowing plasma froze into the confined composite particles that would become the bedrock of all visible matter. This symmetry breaking did not create a new force, but it fundamentally altered the stable, low-energy state of the universe. It determined that the only permissible structures under the strong force would be color-neutral combinations. A proton, for example, contains 3 quarks whose color charges combine to neutral, or white, much like how red, green, and blue light combine to make white light. This confinement transition gave the universe its atomic scaffolding. Without it, quarks would never have clustered into the protons and neutrons that form atomic nuclei. There would be no elements, no chemistry, no solidity. The transition from a symmetric plasma to a confined reality was the moment the ingredients of the cosmos were permanently packaged into the durable units that could later assemble into everything we see and touch. It was the final, crucial step in forging the stable matter that would one day coalesce into the first stars. This cascade of cosmic freezes left behind a permanent record, a faint afterglow that we can still detect today. It is called the cosmic microwave background radiation, and it is the oldest light in the universe. Think of it as a fossilized snapshot of the cosmos when it was only 380,000 years old, a mere infant compared to its current age of over 13 billion years. Before this moment, the universe was an opaque, searing fog of charged particles and light. Photons could not travel freely, as they were constantly scattered by electrons. But as expansion continued to cool the cosmos, it finally reached a temperature where electrons could combine with protons to form the first neutral hydrogen atoms. In an instant, the fog cleared, the universe became transparent, and those once trapped photons were suddenly set free on a journey across space and time. That first flash of clear light has been traveling ever since, stretched by the expansion of the universe from visible light into the microwave part of the spectrum. This is the cosmic microwave background we detect with our most sensitive radio telescopes. It is not coming from stars or galaxies. It is the cooled remnant of the primordial fireball itself, bathing the entire sky in a whisper of radiation just a few degrees above absolute zero. Its most stunning feature is its profound uniformity. No matter where you point your telescope, the temperature of this background glow is almost exactly the same, to within a few 10,000ths of a degree. This near-perfect smoothness is the direct evidence that the early universe was a hot, dense, and remarkably uniform plasma, exactly as our theories of a symmetric beginning require. It is the echo of that featureless plane before the first cracks appeared. But if it were perfectly smooth, we would not be here to observe it. The universe would have remained a featureless soup of hydrogen and helium forever. The magic and the evidence for our entire story lies in the tiny imperfections. When we create exquisitely detailed maps of this cosmic afterglow, we see that it is not perfectly uniform. It is mottled with minute temperature variations, patches that are ever so slightly warmer or cooler than the average. These anisotropies are not random noise. They are the gravitational fingerprints of the early universe. Slightly denser regions where matter had begun to clump appear as slightly cooler spots in the background because photons had to climb out of a slightly stronger gravitational well, losing a tiny bit of energy in the process. These minute fluctuations on the order of 1 part in 100,000 are the cosmic seeds, and they are a direct observational relic of the symmetry-breaking events we have been discussing. Specifically, they are the quantum fluctuations from the inflationary epoch, the microscopic jitters in the inflattened field, stretched to cosmic proportions during that period of hyper-expansion. Inflation took these quantum seeds and imprinted them onto the fabric of space-time. When the universe became transparent hundreds of thousands of years later, those imprints were frozen into the distribution of matter and, consequently, into the temperature map of the cosmic microwave background. This is our most powerful evidence. The pattern of hot and cold spots we see today is a direct photograph of the quantum mechanical tremors that occurred during the universe's first symmetry-breaking phase transition. It is the blueprint from which all cosmic structure was built. Every galaxy cluster, every spiral arm, every star system traces its origin back to one of those subtle wrinkles in the ancient light. In this faint microwave whisper, we are not just hearing the echo of the Big Bang. We are reading the first lines of the cosmic story, written in the language of broken symmetry. But a theory is only as strong as its predictions. The entire narrative of cosmic symmetry breaking, from the Higgs field to the quark gluon plasma, would remain a beautiful story if it could not be tested. The challenge is that these events occurred under conditions of energy and density that seem forever out of reach, locked in the distant past. Yet, science has found a way to turn back the cosmic clock, not by traveling through time, but by recreating those primordial conditions in the laboratory. This is the monumental purpose of particle accelerators like the Large Hadron Collider. Nestled deep beneath the border of France and Switzerland, this 17-mile ring is not just a machine. It is a time machine. By accelerating protons to over 99.9999% the speed of light and smashing them together head-on, the collider concentrates an immense amount of energy into a vanishingly small point. For a fleeting instant in the heart of those collisions, the temperature soars to over 10 trillion degrees Celsius. This is more than 100,000 times hotter than the core of our Sun, and it recreates, in a microscopic fireball, the conditions that existed a fraction of a second after the Big Bang. In these brief, brilliant flashes, the symmetries of our current, frozen universe are momentarily restored. The Higgs field's influence is overwhelmed by the sheer energy, and particles shed their masses, behaving as they did in that early, unified state. Scientists then watch with immense detectors, some as large as cathedrals, as this fireball cools and decays in a microsecond, observing the particles that spray out to see how reality refreezes. It is a direct, repeatable experiment on the very phase transitions that shaped everything. The most spectacular success of this approach came on July 4, 2012. After decades of searching, physicists at CERN announced they had discovered a new particle. The data from billions of collisions revealed a clear signal, a resonance that matched the precise predictions for the Higgs boson. This was not just the discovery of another particle. The Higgs boson is the tangible fingerprint of the invisible Higgs field. Think of the field as an ocean and the boson as a ripple on its surface. You cannot see the ocean directly, but if you can create and detect a ripple, you prove the ocean exists. The discovery of the Higgs boson was the direct, experimental confirmation that the Higgs field permeates the universe. It was the smoking gun evidence for the mechanism of electroweak symmetry breaking. It validated the idea that particles acquire mass by interacting with this all-pervasive cosmic medium. Every time the Large Hadron Collider creates and observes a Higgs boson, it is witnessing, in real time, a fragment of the process that endowed the universe with substance. This single discovery connected the dots across billions of years, linking a mathematical concept from the 1960s to a concrete event in the first trillionth of a second of cosmic history. It showed us that the laws we deduce in quiet offices and test in giant tunnels are the same laws that orchestrated the grandest transformation of all. Yet this elegant picture of cosmic freezing has left behind one of the most persistent and profound puzzles in all of modern physics. It is known as the hierarchy problem, and it asks a deceptively simple question. Why is gravity so unimaginably weak? This is not just a casual observation. The difference in strength between gravity and the other forces is not a small factor of 2 or 10. It is a staggering, almost nonsensical number. The electromagnetic force is stronger than gravity by a factor of 1 followed by 36 zeros. To put that into perspective, the entire planet Earth, with its immense mass, is held in orbit around the Sun by gravity. Yet the tiny electromagnetic force in a simple refrigerator magnet can easily overpower Earth's entire gravitational pull and stick to your fridge door. This vast disparity, this cosmic hierarchy of strengths, creates a deep theoretical tension. In our story of symmetry breaking, the Higgs field gave particles mass, which in turn determines how they respond to gravity. But the energy scale at which the Higgs field operates, the energy of the electroweak symmetry breaking, is about 250 times the mass of a proton. Meanwhile, the energy scale where gravity is expected to become as strong as the other forces, known as the Planck scale, is a quadrillion times higher. These two fundamental numbers, which should be related in a natural, unified theory, are separated by an unthinkable gulf. The problem is one of stability. The calculated mass of the Higgs boson, and thus the strength of the Higgs field, is incredibly sensitive to any other particles or energies in the universe. In our current equations, quantum effects from every other particle, including hypothetical particles at the extreme Planck scale, should contribute to the Higgs mass, driving it up to that impossibly high quadrillion value. For the Higgs to remain at its relatively low, observed mass, these colossal contributions from high-energy physics would have to cancel each other out with a precision of 1 part in a quadrillion. It is as if you tried to balance a pencil on its tip on a windy day, and it remained perfectly upright not just for a second, but for the entire age of the universe. This degree of unnatural, perfect fine-tuning seems absurd to physicists. It suggests our understanding is incomplete, that something is missing from the story. The hierarchy problem is not a minor detail. It is a glaring signpost pointing toward new physics, toward a deeper layer of cosmic symmetry we have yet to uncover. One of the most compelling proposed solutions is a concept called supersymmetry. This elegant idea proposes that for every known particle we have discovered, from electrons to quarks to photons, there exists a hidden super-partner particle. The electron would have a selectron, the quark would have a squark, the photon would have a photino. In a supersymmetric universe, these partner particles would have provided a beautiful, natural cancellation for those problematic quantum corrections to the Higgs mass. The contributions from ordinary particles and their superpartners would perfectly balance, effortlessly explaining why the Electroweak scale remains so much lower than the Planck scale. It would represent a profound, hidden symmetry between the two fundamental classes of particles in nature, fermions and bosons. This symmetry would have been manifest in the ultra-high-energy dawn of the universe, only to be broken as the cosmos cooled, with the superpartners acquiring immense masses that have so far kept them hidden from our detectors. The ongoing, intense search for any sign of these superpartners is a direct attempt to solve the hierarchy problem and to find the next chapter in the story of cosmic symmetry breaking. Their discovery would not just add new particles to a chart, it would reveal a more profound, more symmetric underlying order to reality, an order that was temporarily lost in the Great Freezing, but whose mathematical elegance is necessary to explain the very world we see. The fact that we have not yet found them means the mystery deepens, hinting that the universe's initial moments may hold secrets even more surprising than we have dared to imagine. The fine-tuning of the Higgs mass is not the only strange echo from the universe's first moments. When any material undergoes a rapid phase transition, from water freezing into ice to a metal becoming superconducting, the change is rarely perfectly uniform. Imperfections get locked into the new structure, a bubble of air trapped in ice, a crack in cooled glass, a misaligned crystal boundary. These are defects, scars of the transition process. According to our most sophisticated cosmological models, the grand phase transitions of the early universe should have left behind its own set of cosmic scars, known as topological defects. These are not flaws in the usual sense, but permanent, stable structures woven into the very geometry of space-time itself, relics of a more symmetric age that never fully smoothed away. The most famous and fascinating of these theoretical relics are cosmic strings. Picture the universe cooling through a symmetry-breaking transition, like the formation of ice across the surface of a pond. In most places, the new, stable state aligns in the same direction, but in some regions, isolated pockets might get stuck pointing in different directions. Where these misaligned domains meet, a line of tension forms, a boundary that cannot be smoothed out without melting the entire structure back to its symmetric state. In the cosmos, this boundary is not made of ice but of pure energy, a crack in the fabric of reality. A cosmic string is a hypothetical one-dimensional defect, an infinitely long, unimaginably thin filament of concentrated energy, thinner than a proton but with the mass of a mountain range packed into every inch. It is not a string made of anything, it is a flaw in the geometry of space itself. If one were to pass near you, the effect would be profoundly strange. Because the string contains such immense mass energy, it warps space-time around it, but unlike a black hole, its gravitational influence is unique. It would not pull objects toward it in all directions. Instead, due to its extreme linear density, it would create a conical distortion in space. Imagine taking a flat piece of paper, cutting out a thin wedge like a slice of pie, and then taping the edges back together. The paper now has a conical shape. If you drew parallel lines on the original flat paper after the cut and tape, those lines would no longer be parallel, they would bend around the cone's tip. A cosmic string does this to space. If one passed between you and a distant star, the starlight would travel along this bent geometry, creating two images of the same star, a gravitational lensing effect, but in a perfect distortion-free double. The string itself would be invisible, but its ghostly fingerprint would be written in the sudden duplication of distant galaxies. While cosmic strings have not yet been observed, their potential discovery would be monumental. It would be a direct, observational smoking gun for a specific type of symmetry-breaking event in the early universe. The properties of a detected string, its tension, its behavior, would tell physicists exactly which phase transition created it and at what energy scale. It would be like finding a fossilized air bubble in ancient ice, revealing not just that the water froze, but the precise atmospheric conditions at the moment it turned solid. Other, even more exotic defects are theorized, like domain walls, two-dimensional sheets separating regions of space with different vacuum properties, or magnetic monopoles, isolated north poles without a south. Many models suggest our universe avoided creating these more disruptive defects, which is fortunate, as a single domain wall could have gravitational effects capable of tearing large-scale structure apart. The fact that we do not see them is itself a clue, helping to rule out certain models of cosmic evolution. The search for cosmic strings continues through meticulous analysis of the cosmic microwave background for telltale temperature steps and through surveys of distant galaxies looking for those perfect paired images. Finding one would be more than just adding a new object to the cosmic zoo. It would be touching a fossil from the instant the universe chose its fundamental rules, a permanent scar from the moment symmetry broke and our reality was born. Our universe appears to have settled into one very specific, stable arrangement of forces and particles. But what if this arrangement is not the only possible outcome? What if our cosmic freeze was just one possibility among an almost infinite array of others? This is the radical idea emerging from our most ambitious attempt at a theory of everything, string theory. It proposes that the stable state our universe settled into, the specific way our symmetries broke, is not unique. Instead, there could be a vast and staggering landscape of possible stable vacuum states. In this context, a vacuum state is not just empty space. It is the lowest energy, most stable configuration that the fundamental fields of the universe can adopt after a symmetry-breaking transition. Think of it like the many different ways a complex material can crystallize. Water can freeze into many types of ice, each with a different crystalline structure under different conditions of pressure and temperature. In the same way, the equations of string theory suggest the underlying stuff of reality could have frozen into a truly astronomical number of different stable configurations. Each configuration in this cosmic landscape would represent a universe with a completely different set of broken symmetries. In one valley of this landscape, the Higgs field might have settled at a different value, making electrons 1,000 times heavier and preventing atoms from ever forming. In another, the strength of the strong nuclear force could be weaker, so protons and neutrons never bind, and atomic nuclei are impossible. In yet another, the cosmological constant, which drives the acceleration of the universe's expansion, might be so large that space tears itself apart instantly, or so negative that it recollapses immediately after the Big Bang. Our universe, with its particular forces, particle masses, and cosmological constant, would simply be one point in this inconceivably vast terrain of possibilities. This leads to a profound and deeply controversial implication, one that reshapes how we think about our place in the cosmos. If this landscape is real, then the specific laws and constants of our universe may not be the inevitable, finely tuned product of a single, elegant master equation. They could be the random outcome of a single symmetry-breaking event that happened to roll our particular patch of reality into one particular valley, one stable vacuum state, out of countless trillions of others. This is the multiverse hypothesis in one of its most concrete scientific forms. In this view, the Big Bang was not a unique beginning, but a local event within a much larger, perhaps eternal, meta-reality. Different regions of this greater whole could have undergone different symmetry-breaking transitions, cooling into different vacuum states with completely different physical laws. We exist in a bubble universe that, by sheer chance, has the right combination of broken symmetries to allow for atoms, stars, planets, and life. other bubbles with different laws might be utterly barren or filled with forms of matter and energy we cannot even conceive. This idea is as humbling as it is unsettling. It suggests that the deep questions of why our constants have the values they do, why gravity is so weak, why the electron has its specific mass may have no deeper answer than chance. We are not living in a universe designed with life in mind. We are living in one of the rare universes within a vast multiverse, where the cosmic dice happen to roll a combination that permits complexity to arise. For some scientists, this feels like a cop-out, a retreat from the traditional goal of physics to find a single, beautiful, unique explanation for reality. For others, it is a necessary and elegant extension of the logic we have already seen. If symmetry breaking is the mechanism that generates diversity from unity, and if the underlying theory allows for many possible broken states, then a multiverse is not a wild speculation, but a natural prediction. The search is now to find any possible signature, any faint imprint on our cosmic microwave background or in the distribution of galaxies that could hint at a collision with another cosmic bubble with different laws. Until then, the landscape remains a breathtaking mathematical possibility, a reminder that the story of symmetry breaking may not have just shaped our universe, but could be the engine generating an endless tapestry of realities, most of which we will never see. This cascade of cosmic freezes may have done more than define our physical laws. It could have established the very direction of time itself. We all intuitively feel time's arrow. An egg splatters on the floor, but the mess never spontaneously reassembles into a whole egg. Memories are of the past, never the future. The universe moves from order to disorder. This relentless march is governed by the second law of thermodynamics, which states that entropy, a measure of disorder or randomness, always increases in a closed system. But why was the entropy of the universe so incredibly low in the first place? Why did it start in such an exquisitely ordered, low entropy state? The answer may be found in the story we have just traced. That initial moment of near-perfect symmetry was a state of supreme order. The universe was uniform, smooth, and homogeneous. In thermodynamic terms, this is a configuration of fantastically low entropy. There were no temperature differences, no clumps of matter, no complex structures, just a featureless sea of energy. This was the most ordered state the cosmos could possibly have. When symmetries began to break, the universe began a one-way journey away from that perfect order. Each phase transition, the separation of forces, the condensation of the Higgs field, the confinement of quarks, locked in new structures and created new distinctions. With every new distinction, the number of possible microstates of the universe increased. Entropy began its inevitable climb. The arrow of time, therefore, may have been set in motion by that first, critical deviation from symmetry. The universe could not stay in that pristine, ordered beginning. It was inherently unstable, destined to roll downhill into a state of greater complexity and ultimately greater disorder. The broken symmetries we see today are not just relics of that fall. They are the permanent signposts pointing from that ordered past toward our increasingly random future. This connection becomes even more profound when we look at the microscopic laws of physics. The equations governing the interactions of particles, for the most part, are time-symmetric. If you filmed two electrons repelling each other and played the film backwards, the reversed motion would also be a perfectly valid solution to the equations. So why does time feel so irreversible in our daily lives? A crucial piece of the puzzle was discovered in the delicate behavior of certain subatomic particles. In the 1960s, researchers studying the decay of particles called kaons found something astonishing. The laws governing this decay exhibited a subtle violation of CP symmetry, the combined symmetry of charge and parity we discussed earlier. Because of a deep theorem in physics, a violation of CP symmetry implies a violation of time reversal symmetry, known as T-symmetry. In essence, the processes involving these particles have a tiny, built-in arrow. They would look slightly different if time were run backwards. This was not a dramatic, large-scale effect, but it was a fundamental crack in the mirror of time at the most basic level of reality. The universe's microscopic machinery is not perfectly reversible. It possesses a faint, inherent bias that distinguishes past from future. This microscopic bias, combined with the macroscopic climb of entropy from a low-entropy symmetric beginning, creates the powerful, one-way flow of time we all experience. Our journey from a unified dawn to a complex and broken present is not just a historical account. It is the very reason we remember yesterday and anticipate tomorrow. The universe's broken symmetries wrote the arrow of time into the foundation of everything, turning a featureless moment of pure potential into a story with a past, a present, and an unknowable future. From that faint cosmic whisper, an entire universe of structure was born. The story of our cosmos is a story of seeds and soil, a tale of how the tiniest quantum imperfections grew into the grandest cosmic architecture. And at the heart of it all lies the unifying thread of symmetry breaking. It provided both the seeds and the very laws that allowed them to grow. The chain of creation begins with the inflationary epoch, that moment of hyper-expansion driven by its own symmetry-breaking field. As we saw, the quantum jitters in that field were stretched from the microscopic to the cosmic scale, creating minute variations in the density of the primordial universe. When inflation ended, these variations were frozen into the fabric of space-time itself. Hundreds of thousands of years later, when the universe became transparent, these density differences were imprinted as the subtle hot and cold spots we now see in the cosmic microwave background. This ancient light map is not just a relic, it is the original blueprint, the gravitational template for everything to come. Those slightly denser patches, appearing as cooler spots in the microwave sky, held an infinitesimally stronger gravitational pull. They were the cosmic seeds, but seeds alone are not enough. For a garden to grow, you need fertile soil and the right set of natural laws. This is where the later symmetry breakings entered the stage, writing the rulebook for how these seeds would evolve. First, the quark confinement transition forged stable protons and neutrons from the primordial plasma, creating the normal, baryonic matter that would eventually glow as stars. But another, more mysterious component was also at play: dark matter. While its exact nature is still unknown, it is thought to be a relic particle from an even earlier symmetry-breaking event, a stable remnant that interacts only through gravity. Because dark matter does not feel electromagnetic forces, it was unaffected by the intense pressure of radiation in the early universe. It could begin collapsing under its own gravity long before normal matter could. Those primordial density seeds acted as focal points. Dark matter began to pool into these slight gravitational wells, forming vast, invisible scaffolds, halos, and filaments in an emerging cosmic web. This dark matter architecture provided the gravitational backbone for everything else. Then, governed by the laws of electromagnetism and nuclear forces established by earlier symmetry breaks, normal matter could follow. Hydrogen and helium gas, now cooled and neutral, felt the pull of these growing dark matter concentrations. It streamed along the invisible filaments, pooling at the nodes of the web. Inside these deepening wells of gravity, gas clouds compressed, heated, and eventually crossed the threshold for nuclear fusion. The first stars ignited, violent and brilliant, forging heavier elements in their cores. Their light reionized the cosmic fog, and their explosive death seeded space with the elements for planets and life. These first stars gathered, drawn by the same gravitational template, into proto-galaxies. Over billions of years, mergers and accretion built the majestic spirals and ellipticals we see today. Every galaxy cluster, every stellar nursery, every solitary star shining in the void can trace its lineage back to that original set of quantum seeds. And those seeds, in turn, were a direct product of a symmetry-breaking event. The specific strengths of the forces, set by how those symmetries broke, dictated how quickly structures could form, how large they could grow, and how stars would burn. Without the strong force confining quarks, there would be no atomic nuclei to gather. Without electromagnetism, there would be no way for gas to cool and condense. Without gravity's specific weakness, structure formation would have happened too rapidly, potentially leading to a universe of only black holes. The breathtaking cosmic web we observe today, with its great walls, vast voids, and brilliant island galaxies, is not a random scattering. It is the final, evolved expression of a pattern written at the beginning of time, a pattern born from imperfection. The universe's journey from perfect symmetry to rich complexity was not a mistake. It was the necessary and beautiful chain of events that turned a featureless fireball into a home for wonders. But the story of symmetry breaking is not confined to the distant past. Its echoes may be shaping the universe's ultimate destiny today. Across the cosmos, astronomers have observed a startling phenomenon. The expansion of the universe is not slowing down, as one might expect from the gravitational pull of all its matter. It is speeding up. Some mysterious repulsive force, which we call dark energy, is pushing galaxies apart at an ever-increasing rate. This discovery reshaped our cosmic timeline and poses a profound modern question. Could dark energy itself be a manifestation of symmetry, or its breaking playing out on the grandest stage? One leading explanation is that dark energy is simply the cosmological constant, a term Albert Einstein first introduced into his equations of gravity. In this view, it is not a force in the traditional sense, but a fundamental property of empty space itself. Even in a perfect vacuum, quantum theory tells us that virtual particles flicker in and out of existence. This gives the vacuum a baseline energy, a constant pressure inherent to the fabric of reality. If this vacuum energy is positive, it exerts a gentle, repulsive push on space itself. This idea connects directly to our earlier story. The value of this cosmological constant would have been set during the earliest symmetry-breaking phase transitions, frozen into the universe just like the strengths of the forces and the masses of particles. It would be a permanent, low-energy remnant of that primordial freeze. In this scenario, dark energy is not an active process, but a silent signature of a long-completed event, a number written into the cosmic code at the beginning. Yet its constancy is what makes it so powerful over time. In the early, dense universe, its effect was negligible, overwhelmed by the gravity of radiation and matter. But as the universe expanded and thinned out, matter's gravitational grip weakened. Eventually, the steady, unyielding push of the vacuum energy became dominant. The symmetry, or perhaps the specific broken symmetry that determined this value, is now dictating the future of everything. It is as if a rule established in the first moments has finally, after billions of years, taken command of the cosmic helm. However, another compelling possibility exists. What if dark energy is not a constant but something dynamic? Some theories propose it could be a modern form of a symmetry-breaking field, similar to the Higgs field or the inflaton, but acting on a cosmological timescale. Physicists call this concept quintessence. Imagine a new cosmic field that has been slowly evolving since the dawn of time. For most of cosmic history, it was trapped in a high-energy state, its influence dormant. But as the universe expanded and cooled past a certain threshold, this field may have begun a slow roll toward its true, stable minimum. This rolling could represent a symmetry breaking happening now, in the present cosmic epoch. The energy released by this incredibly gradual transition would permeate space, acting as a repulsive force. Unlike a true constant, the strength of quintessence could change over time, potentially increasing or even fading away in the far future. This idea is thrilling because it suggests the laws of the universe are not entirely fixed. The symmetries we observe today might still be evolving. The vacuum of space, which we think of as empty and passive, could be an active participant in an ongoing cosmic transformation, one that began with the Big Bang and continues to this very moment. The ultimate fate of the cosmos hinges on which of these pictures is true. If dark energy is a true cosmological constant, then the acceleration will continue forever. Billions of years from now, as space stretches at an ever faster rate, distant galaxies will be pushed beyond our observational horizon, their light never able to reach us. Our local group of galaxies will merge into one giant elliptical galaxy, isolated in an ever-expanding void. The distant universe will fade to black, leaving future cosmologists with a sky nearly empty of galaxies, a lonely and silent end. If, however, dark energy is a dynamic field like quintessence, the future could be far more uncertain and perhaps more dramatic. The field could eventually decay, causing the acceleration to stop or even reverse, potentially leading to a cosmic collapse. Or it could grow stronger, leading to a scenario so extreme it has been dubbed the Big Rip, where the repulsive force becomes so powerful it tears apart galaxies, solar systems, and even atoms themselves. While this sounds unsettling, it is framed here as a natural cosmic process, a potential consequence of the universe's underlying physics playing out over inconceivable timescales. Our investigation into the first moments of time has therefore brought us face to face with the universe's final chapter. The same fundamental principles, symmetry, stability, and the breaking of perfection, that ignited the chain of creation may now be guiding its long-term evolution. Whether dark energy is a frozen relic or an active, breaking field, it ties the universe's birth to its destiny. In seeking to understand the origin of everything, we have inadvertently begun to read its last page. Yet for all its explanatory power, this grand narrative of cosmic freezing faces profound challenges. The most formidable is the sheer inaccessibility of the energies involved. While the Large Hadron Collider can recreate the conditions of the Electroweak symmetry breaking, allowing us to study the Higgs field, the earlier and more dramatic transitions remain out of reach. The energy scale of the grand unified theory transition, where the strong force separated, is about 1 trillion times more powerful than anything our most advanced machines can produce. We are left with elegant mathematics and compelling indirect evidence, but we cannot recreate that moment in a lab or directly observe its relics. This forces cosmology into the realm of historical detective work, where we must infer the events of the first second from the faint clues left billions of years later. The theory of cosmic inflation, which solves so many puzzles, faces a similar test. While its predictions for the cosmic microwave background have been stunningly accurate, the inflattened field itself remains hypothetical. We see the effects, the uniformity, the flatness, the pattern of seeds, but we have not detected the field or its particle directly. Proving inflation happened is like finding a perfectly arranged garden, and deciding a master gardener must have prepared the soil without ever seeing the gardener or their tools. The search continues, with scientists scrutinizing the microwave background for specific, predicted patterns called primordial gravitational waves, which would be the definitive signature of inflation's violent stretching of space-time. Until such a signal is found, even this cornerstone of modern cosmology rests on compelling but incomplete evidence. Beyond these experimental hurdles, the entire framework of symmetry breaking is not the only story being told. Some physicists propose radically different cosmic origins that reinterpret or even bypass the need for these sequential freezes. One prominent alternative is the concept of a cyclic universe. In this model, the Big Bang was not a singular beginning from nothing, but a phase in an endless cycle. The universe expands from a hot, dense state, much as we observe, but dark energy eventually decays. The expansion slows, halts, and reverses in a big crunch. Instead of collapsing to a point of infinite density, a cosmic bounce occurs, perhaps through processes in string theory or quantum gravity, transforming the collapsed universe into a new expanding one. In this view, our universe is one chapter in an infinite book. The symmetries we see broken might not be the result of a one-time freeze from a unique beginning, but could be reset or reconfigured with each new cycle. The smoothness and uniformity we attribute to inflation could instead be the result of the universe being stretched and smoothed over an eternity of previous cycles. This idea challenges the linear narrative of a single, definitive symmetry breaking cascade, suggesting instead a cosmos of eternal return. Another frontier of thought questions the very nature of space and time. The idea of emergent spacetime suggests that the dimensions we experience, the three of space and one of time, are not fundamental. They might arise from a more basic, non-spatial reality, much like the smooth surface of a lake emerges from the chaotic interactions of countless water molecules. In such a framework, the concept of a symmetry breaking in space and time may not apply at the very beginning, because space and time as we know them would not have existed yet. The forces and particles we see might emerge together with the geometry of the cosmos from a more primitive, information-based substrate. This is not a rejection of symmetry breaking, but a potential deepening of its context. The symmetries that broke to give us our familiar laws might be shadows of deeper, more abstract symmetries in a realm before space and time. These alternatives remind us that our story, for all its coherence, is a map drawn from the territory we can observe. The true cosmic landscape may hold features our current maps cannot yet chart. The ongoing quest is not to discard the powerful idea of symmetry breaking, but to discover whether it is the final answer or a brilliant clue pointing toward an even more profound beginning. This staggering precision in the laws of nature brings us to a haunting question that has echoed through physics for decades. Why does our universe seem so perfectly tailored for life? The specific outcomes of those early symmetry-breaking events were not arbitrary. They set numbers, constants, that appear to be exquisitely fine-tuned. Change any one of them by even a tiny fraction, and the entire cosmic story collapses into silence. For example, if the strong nuclear force were just a few % stronger, protons would bind so tightly that all the hydrogen in the early universe would have fused into heavier elements. There would be no hydrogen left to fuel the long, stable lives of stars like our Sun. If it were slightly weaker, protons could not form at all, and atomic nuclei would never exist. The force of gravity, that incomprehensibly weak pull, is also set on a knife's edge. If it were stronger, stars would burn their nuclear fuel far too quickly, flaring out before life could evolve on any orbiting planets. If it were weaker, matter would never have clumped together to form stars and galaxies in the first place. Even the amount of dark energy is bizarrely precise. If it were slightly larger, the universe would have expanded so rapidly after the Big Bang that no galaxies could have ever condensed from the cooling gas. If it were slightly smaller, the cosmos would have recollapsed on itself long before life had a chance to emerge. This is known as the fine-tuning problem. The universe did not just break its symmetries, it broke them in one very specific way, a way that miraculously allows for atoms, chemistry, planets, and ultimately, observers like us to wonder about it all. This apparent tuning feels like more than a coincidence. It feels like a signature. So what does it mean? Physicists grapple with three profoundly different interpretations, each with implications that reshape our understanding of reality. The first possibility is that there is a deeper, unifying law we have not yet discovered. Perhaps the constants are not free parameters to be set by chance, but are the inevitable, unique outcome of a more fundamental theory, like string theory or a theory of quantum gravity. In this view, the universe could not have been any other way. The tuning is not a puzzle to be solved, but a consequence of a deeper mathematical necessity we have yet to uncover. The second and more controversial idea is the multiverse selection effect we touched on earlier. If a vast landscape of possible universes exists, each with different broken symmetries and different physical constants, then of course we find ourselves in one of the rare ones that can support complex life. We are not seeing a tuned universe. We are seeing the only kind of universe we could possibly observe. In this cosmic lottery, trillions of barren universes may exist for every one that can host a single atom. Our presence here is not evidence of design, but simply a consequence of our own existence as observers. We are the winners of a colossal existential dice roll. The third possibility is the most unsettling of all. Perhaps it really is just a staggering, incomprehensible coincidence. A single, random roll of the cosmic dice in a one-shot universe, and we got astronomically lucky. This idea offers no deeper explanation, and for many scientists that feels deeply unsatisfying. It leaves the most profound question of existence unanswered. These are not merely academic debates. They strike at the heart of why the universe is the way it is, and whether our quest for meaning has a foundation in physical law. The fine-tuning problem transforms the story of symmetry, breaking from a historical account into a personal one. The specific flaws that appeared in the cosmos's first moments were not just interesting. They were necessary. They wrote a rulebook that allowed for carbon atoms to form in dying stars, for water to flow on rocky worlds, and for consciousness to eventually arise and gaze back at the stars, wondering how it all came to be. Whether this points to a deeper law, a multiverse, or pure chance remains one of the most profound and unresolved mysteries in all of human thought. The same principles that sculpted the cosmos are at work in the world around you, hidden within the materials of everyday life. To truly grasp the universe's grand transformations, we can look closer to home at the strange and beautiful behaviors of matter itself. Consider an ordinary bar magnet. At a high temperature, it is just a piece of metal. Its atoms are jostling with thermal energy, and their tiny internal magnetic moments, like microscopic compass needles, point in random directions. The system is symmetric. There is no preferred north or south, but cool that metal below a specific critical temperature, known as the Curie point, and something remarkable happens spontaneously. Without any external command, vast numbers of these atomic compass needles suddenly align in the same direction. They choose a specific orientation, breaking the rotational symmetry of the material. The metal is now ferromagnetic. It has a north and a south pole, and it can attract other metals. A new property, magnetism, has emerged from the collective behavior of the system. This is not a cosmic event, but it is governed by the same fundamental physics. The symmetric, disordered state became unstable as energy was removed, and the system settled into a new, stable state with less symmetry and a dramatic new emergent quality. The direction chosen is arbitrary. The magnet could have polarized north-south or east-west, but once the choice is made, it defines the material's reality. This is spontaneous symmetry breaking in a form you can hold in your hand. We see this pattern repeat in some of the most technologically wondrous materials known to science. Take superconductivity. In an ordinary metal, electrons bump and scatter off atoms, creating electrical resistance. But cool certain materials to extremely low temperatures, and they undergo a phase transition into a superconducting state. In this new phase, a profound symmetry is broken. Electrons, which normally repel each other due to their negative charges, pair up in a coordinated dance described by quantum mechanics. These Cooper pairs, as they are called, can move through the material as a single, coherent quantum fluid. The symmetry that breaks here is more abstract, related to the phase of the electron wave functions. Before the transition, this phase is random and undefined. After the transition, the phase locks into a single, coherent value across the entire superconductor. This broken symmetry leads to the emergent properties of zero electrical resistance and the expulsion of magnetic fields, known as the Meissner effect, where a magnet can levitate above the cooled material. The material did not simply get colder, it entered an entirely new organizational state with laws of its own, all because a symmetry was spontaneously lost at a critical threshold. The phenomenon is equally vivid in liquid crystals, the substances that make your digital watch or flat-screen monitor possible. In their high-temperature isotropic phase, the long, rod-like molecules are oriented randomly, like toothpicks spilled on a table. This state is fully symmetric. It looks the same from every angle, but as the liquid cools, it can enter a nematic phase. Here, the molecules spontaneously align along a common direction, called the director. The system has broken its rotational symmetry. It now has a distinct orientation, though the molecules are not locked into fixed positions and can still flow like a liquid. This broken symmetry gives liquid crystals their unique optical properties, allowing them to precisely control the passage of light when a small electric field is applied. The transition creates a new realm of behavior between liquid and solid, a direct consequence of molecules collectively choosing an order that did not exist before. These earthly examples are more than just analogies. They are the same physics playing out on a human scale. The mathematical framework that describes a magnet choosing its polarity is fundamentally the same as that which describes the Higgs field choosing its value across the universe. In each case, a system with many interacting components reaches a point where its symmetric state is no longer stable. As a control parameter changes, often temperature, the system undergoes a phase transition and settles into a new, stable state with less symmetry. This new state possesses emergent properties that were simply not present, not even in principle, in the old one. Magnetism, superconductivity, and liquid crystalline behavior are not properties of individual atoms or electrons. They are collective phenomena that arise only when the symmetry breaks and the system organizes itself. In the cosmos, the control parameter was the expanding, cooling universe. The interacting components were the fundamental fields and forces, and the emergent properties were the distinct laws of physics, particle masses, and the very possibility of structure. By studying a magnet cooling on a lab bench, we are running a scaled-down experiment of the primordial cosmic freeze. Each time a symmetry breaks, whether in a crystal forming from a melt or in the vacuum of space itself, it opens a door to a new world of possibilities, crafting complexity from simplicity right before our eyes. This cascade of cosmic accidents forces us to confront a deep philosophical question. If our fundamental laws are not eternal truths, but frozen outcomes of ancient chance events, what does that say about the nature of reality itself? For centuries, science has sought immutable laws, a fixed and timeless rulebook written into the fabric of existence. We imagined a universe governed by mathematical necessity, where every outcome was dictated by elegant, unbreakable equations. The story of symmetry breaking challenges that vision at its core. It suggests that what we call the laws of nature may not be the authors of the cosmic story, but characters within it. They are not the director of the play, but actors who showed up for the audition, got the part, and have been performing ever since. The shift from a state of pure potential to our concrete reality was not a logical deduction. It was a historical occurrence, a specific sequence of events that could, in principle, have unfolded differently. This introduces a powerful idea: contingency. Our universe is contingent, meaning it depends on a series of prior conditions that did not have to be this way. The strength of gravity, the mass of the electron, the existence of 3 generations of particles, these are not inevitable. They are the particular results of a specific cosmic freeze. This transforms our understanding from a universe of necessity to a universe of history. We are not living in the only possible cosmos dictated by pure logic. We are living in the one that actually happened, with all its unique and idiosyncratic rules. This realization carries a profound sense of both humility and wonder. It humbles us because it removes any special, preordained status for our particular set of physical constants. There is no mathematical proof that demands our universe must exist as it does. Yet it inspires wonder because it means our reality is a genuine artifact, a specific creation with a narrative. The cosmos has a biography, not just a blueprint. It went through a childhood of rapid change and settled into the adult it is today. This narrative quality makes the universe feel more like a story to be discovered and less like a static equation to be solved. It places us as conscious observers within an unfolding epic that began with a symmetry-breaking cascade and led, through billions of years of consequence, to beings capable of tracing that very path. The question of why these specific breaks happened, why this particular valley was chosen, then becomes the central mystery. Is there a deeper principle that selected this outcome, or are we simply witnessing the ultimate roll of the dice? This tension between chance and necessity lies at the heart of modern cosmology. Some physicists hold out hope for a theory so profound that it uniquely predicts our universe, making the apparent contingencies into inevitabilities. Others see the multiverse landscape as the only natural explanation, where chance operates on a canvas of infinite possibilities. Both answers reshape our place in the cosmos. If our laws are necessary, we live in a universe of profound, hidden order. If they are contingent, we live in a universe of breathtaking, creative accident. Either way, the act of symmetry breaking stands as the pivotal moment that translated abstract potential into tangible reality. It gave the universe its character, its rules, and its capacity for stories, including the story of life, wondering how it all came to be. The story of symmetry breaking is a triumph of modern cosmology, but it is far from finished. Every answer it provides seems to open a door onto a new, deeper mystery. What was the initial trigger, the first push that sent the universe tumbling from its state of perfect symmetry? Our equations describe the instability, the ball rolling down the hill, but they do not yet tell us what placed the ball so precariously at the summit in the first place. Was it an inherent property of the unified field, a mathematical inevitability, or did some event, perhaps even a fluctuation from a prior state of reality, provide the necessary nudge? This question pushes us to the very edge of physics, to the moment where time and space as we know them may have flickered into existence. It hints that the symmetries we have traced may themselves be broken fragments of something more profound and more elegant, a deeper order that existed before our cosmos began. Could the forces and particles we see be the result of a symmetry breaking from a more abstract, perhaps geometric, foundation? Theories like string theory suggest exactly this, proposing that all particles are vibrations of tiny, multidimensional strings, and that the specific pattern of vibrations we see is just one possible stable configuration, one valley in a vast cosmic landscape. This implies there could be layers of symmetry we have not yet glimpsed, mathematical harmonies that were lost in the first unimaginable flash, whose echoes we are only now beginning to decipher. To move from speculation to knowledge, we must find ways to test these ideas directly. The greatest challenge is that the most dramatic events occurred at energy scales far beyond anything we can recreate. The grand unified theory transition, where the strong force peeled away, happened at energies 1,000,000,000,000 times more powerful than the Large Hadron Collider can achieve. We cannot build a machine that big, not on Earth, so we must become cosmic archaeologists searching for permanent relics from those epochs. One of the most promising searches is for primordial gravitational waves. Inflation, the period of hyper-expansion, should have sent powerful ripples through the fabric of space-time itself. These waves would have left a distinct, swirling pattern in the polarization of the cosmic microwave background, a faint fingerprint called B modes. Detecting this signal would be a direct confirmation of inflation and would tell us the energy scale at which it occurred, offering a glimpse into physics at nearly the duty scale. Next-generation observatories, like the Simons Observatory in Chile and the proposed Light-Bird satellite, are being designed with exquisitely sensitive detectors to scan the ancient microwave sky for this elusive pattern. Finding it would be like hearing the faint echo of the universe's first violent growth spurt. Alongside peering into the ancient light, we are building new ears to listen to the ripples in space-time today. Ground-based detectors like LIGO and Virgo have opened the window on gravitational waves from merging black holes and neutron stars. Future space-based observatories, such as the European Space Agency's LISA mission, will listen for lower frequency waves from even more colossal events, like the mergers of supermassive black holes. But they might also hear something else, the cosmic symphony of a first-order phase transition in the early universe. Some theories suggest that when certain symmetries broke, they did so not smoothly, but violently, with bubbles of the new vacuum nucleating and colliding in the primordial plasma. These collisions would have been cataclysmic, sending powerful gravitational shock waves across the cosmos. LISA could, in principle, detect the faint, characteristic hum of such an event, a direct recording of a symmetry breaking from the first second of time. It would be a sound from the creation of the forces themselves. On the particle frontier, the quest continues for the next layer of reality. While building a collider powerful enough to reach duty energies is impossible, we can search for indirect signatures. The decay of the proton, a process predicted by many grand unified theories, would be a monumental discovery. Our current understanding says protons are stable, but if the strong force was once unified with the electroweak force, there might be extremely rare channels through which a proton could decay into lighter particles. Enormous, ultra-sensitive experiments like Hyper-Kamiok and in Japan will monitor vast tanks of pure water, waiting to catch the telltale flash of light from a single decaying proton among countless trillions. Observing even one such event would revolutionize physics, providing direct evidence for unification and giving us a key to the energy scale of that first great separation of forces. Similarly, the hunt for dark matter particles and for any sign of supersymmetry continues at colliders and deep underground laboratories. Discovering a particle that solves the hierarchy problem would not just complete the standard model, it would reveal a profound symmetry between force and matter particles that was present at the beginning and then hidden. A symmetry whose breaking gently sculpted the mass of the Higgs boson and made our universe possible. Each of these experiments, the telescopes scanning the primordial sky, the gravitational wave antennas listening to space-time, the detectors waiting for a proton to vanish, is a thread reaching back across 13.8 billion years. They are not separate endeavors, they are parts of a single, unified probe into the conditional nature of our reality. They seek to answer whether our cosmic freeze was a unique, finely tuned event, or one of countless outcomes in a multiverse landscape. The data we gather in the coming decades will either reveal new, deeper symmetries that guide us toward a final theory, or it will solidify the picture of a contingent, historical universe whose laws are frozen accidents of a distant, unrepeatable moment. Either outcome will fundamentally alter our story. We are no longer just reconstructing cosmic history from its remnants. We are actively testing the very foundations of that history, seeking to understand not just how our universe broke its symmetries, but why it broke them in this one peculiar, fruitful way. The next chapter of this story will be written not in the distant past, but in the data streams of machines we are building right now. The universe's story is not a collection of random events, but a single, elegant cascade. Each broken symmetry set the stage for the next, progressively carving a habitable reality from a state of pure potential. The timeline begins with the most profound instability of all, the inflationary epoch. As the inflattened field broke its symmetry and rolled to its stable state, it unleashed a burst of expansion that stretched a quantum seed to cosmic proportions, creating a vast, smooth, and flat arena. This prepared a uniform stage, but it was still a stage without actors or a script. The next act introduced the players. As the universe cooled further, the grand unified force could no longer hold. Its symmetry shattered, peeling the strong nuclear force away from the still unified electroweak force. This first major division established a fundamental border in the laws of physics, creating the rule that would later allow quarks to bind into permanent protons and neutrons. The cosmos now had distinct domains, but its particles remained massless phantoms, zipping at light speed. Then came the pivotal moment that gave substance to the drama. The Higgs field, permeating the cooling vacuum, underwent its own transition. Settling into a non-zero value everywhere, it broke the electroweak symmetry, splitting the unified force into the electromagnetic and weak forces we know today. More crucially, it endowed quarks and electrons with mass. Suddenly, particles had weight and inertia. They could slow down, interact, and clump. The universe gained texture. Yet a critical danger remained. The quark-gluon plasma, a seething soup of free ingredients, was still too hot to form stable matter. As temperatures plunged past 2 trillion degrees, the strong force enacted its final, confining rule. The symmetry of free color charge was broken. Quarks and anti-quarks were suddenly and permanently locked into composite particles, protons, neutrons, and mesons. The building blocks of atomic nuclei were now forged, durable and ready for assembly. But the stage was still empty of lasting structures. The final, delicate symmetry to break was that between matter and antimatter. Through a subtle violation known as CP Symmetry, processes in the cooling plasma favored matter by just 1 part in a billion. When the great annihilation finished, that tiny surplus was all that remained, the precious residue from which every star, planet, and living thing would eventually be built. Each event was a necessary condition for the next. Inflation created a smooth, large universe. Force separation established the rulebook. The Higgs mechanism gave particles mass so they could gravitate. Quark confinement packaged that mass into stable units, and matter-antimatter asymmetry ensured there was something left to package. This sequential freezing did not just create a universe. It crafted a very specific kind of universe, one with stable nuclei, complex chemistry, and gravitational wells deep enough to form stars but gentle enough to let them burn for billions of years. The initial uniformity was not erased but transformed. Its perfect symmetry, now hidden, is the silent foundation upon which all this beautiful, structured complexity rests. We are not the result of a single miracle, but of a chain of cosmic necessities, each broken symmetry handing off a more structured world to the next. From a state of pure, featureless potential, our universe gained its character through a series of creative imperfections. Symmetry breaking is not a footnote in cosmic history, it is the central narrative. It is the fundamental creative process that translated the unity of the Big Bang into the breathtaking diversity we witness today. Every physical law we take for granted, every particle with mass, every galaxy spinning in the void, is a direct consequence of that initial, necessary shattering of perfection. What began as a single, unified superforce fractured into the 4 distinct interactions that govern reality. What was once a sea of identical particles acquired unique identities, masses, and charges. What was a perfectly smooth expanse developed the subtle wrinkles that grew into the cosmic web. This cascade of cosmic freezes did not destroy the initial symmetry, it hid it, locking its elegant mathematics beneath the surface of our complex, broken world. We are not living in a universe of static, eternal laws. We are living in the outcome of a story, a specific sequence of historical events that chose one path from an infinite field of possibility. This transforms our understanding from a static equation to a dynamic biography. The cosmos has a past, a series of decisions made under extreme conditions, and we are the legacy of those ancient choices. This story invites a profound shift in perspective. It means the constants of nature, the very rules of the game, are not necessarily written in stone for all eternity. They might be the frozen artifacts of a particular cosmic weather pattern in the first fleeting moments. This realization connects us directly to the dawn of time. The carbon in our cells, the iron in our blood, the light from our sun, all exist because of a specific pattern of broken symmetries. We are not just observers of the universe, we are expressions of its deepest architectural principles. Our ability to ponder these very ideas is a direct product of a universe that broke its symmetries in just the right way to allow for complexity, chemistry, and consciousness. So the next time you look up at the night sky, remember you are not looking at a distant, separate cosmos. You are looking at the evolved consequence of its first and most important decisions. The stars are not simply points of light, they are the brilliant evidence of a creative process that turned uniformity into wonder. What does it mean for our place in this story? It means we are woven into the fabric of cosmic history, participants in an epic that began with a single, silent crack in the face of perfection. We would love to hear your thoughts on this incredible journey from unity to diversity. What part of this cosmic transformation resonates most with you? Share your reflections in the comments below, and as always, thank you for exploring the deepest mysteries with us.